Hello and welcome to our DVD on irrigation design fundamentals. Today we'll be reviewing some fundamental concepts in irrigation design to help prepare you for irrigation installation and design. The first thing we're going to talk about is pressure. There are two types of pressure concerning an irrigation system. One is static pressure, and the definition of static pressure is water at rest. An example of static pressure would be putting a pressure gauge onto a hose bib and turning onto the hose bib and taking the reading off your pressure gauge when no water is turned on in the residence. The other type of pressure is dynamic pressure, and that is water in motion. An example of dynamic pressure would be when your sprinkler system is activated and the heads are popped up and water is coming out of the heads. Another term for dynamic pressure on an irrigation system would be actual head pressure. So when the system was running, the actual pressure at the nozzle at the head would be an example of the dynamic pressure. One of the most common ways to create static pressure is by elevation. And the formula to get that static pressure would be taking your elevation and multiplying it by 0.433 to get your static pressure. That's a very important formula to remember when trying to determine static pressure based on elevation. Another formula to get the static pressure would be to take your elevation and divide it by 2.31. And that would also give you a static pressure reading. We'll go over a few examples on using both methods. One example would be if you had a piece of PVC pipe that was 1 inch in diameter and 10 foot tall, and it was standing up with the bottom capped off. If we filled this pipe up with water and wanted to take a static pressure reading at the base, the formula would be to take our elevation, which is 10 feet, and multiply it by 0.433, which will give us 4.33 psi. The size of the pipe would not make a difference in this example. This pipe can be 1 inch pipe, it could be 2 inch pipe, it can even be the diameter as large as you want to go, 12 inch or 14 inch or 16 inch pipe. That does not make a difference on the static pressure. The only thing that makes a difference is the elevation of this pipe. At any time during this DVD, please feel free to stop and rewind and review these concepts. let's say we had another piece of pipe, and again the diameter of the pipe doesn't make a difference, and we'll say this pipe is 2.31 feet tall in elevation from here, from this point to this point. And again, we had the bottom capped off, and we filled this pipe full of water. And we want to know what is the static pressure at the base of this pipe. We do our formula again. 2.31 feet is our elevation times 0.433, and our answer will be 1 psi. And that's the relationship between the 2.31 and the 0.433 and 1 pound of pressure. What this is normally called is foot of head. And again, this is another key term to know, that 2.31 foot of head equals 1 psi. Another example of this would be, say we had a water tower, and this water tower had elevation of water in it that was 100 feet tall. To get our static pressure at the base of this tower, there's two ways we can calculate it. One is we can take our 100 feet times 0.433, which will give us 43.3 psi. The other way is take our 100 feet and divide it by our 2.31 foot of head, and that's also going to give us 43.3 psi. So that's the way to convert elevation into pressure. And this is one way cities create pressure for homes and businesses in their water districts. Another important concept is to know how to convert PSI into elevation. This formula would be to take your PSI and divide it by 0.433, or take your PSI and multiply it by 2.31. An example of this would be, once again, we have a water tower, but now we'll say at the base of this tower we have 120 pounds of static pressure, 120 psi static. Our formula on this would be to take our 120 psi and divide it by 0.433, or we can take our 120 psi and multiply it by 2.31, and we'll get that our water tower is approximately 277 feet tall. So in review, the two types of pressure regarding an irrigation system would be your static pressure. One way to create static pressure is with elevation. Another way to create static pressure would be with a pump, a booster pump or a pump station. And static pressure is water at rest, when it's not moving, not in motion. The other type of pressure would be your dynamic pressure, which is water in motion. And concerning a sprinkler system, that would be the pressure at the actual head when the system is turned on and the water is moving through all the components. The formula to get your dynamic pressure would be to take your static pressure and subtract your total pressure losses through all your irrigation components. Go ahead and get out the first handout that's enclosed in your packet, and you'll see this drawing. You'll need your scale and your calculator to do some of these calculations. Another important factor in irrigation design is slope. On this example, we're going to refer to it as percent of slope. So we have our percent of slope right here. The scale on this particular design is a 1 to 20 scale, so you'll need to get out your engineer scale and turn to the 1 inch equals 20 feet side of it. Our formula for slope to calculate the percent of slope is to take the rise over the run on this design. The rise in this case is going to be the differences in the elevations from point A, B, C, and D. On this design, you'll see we have lines drawn through. These lines are called contour lines. Contour lines. And contour lines represent changes in elevation on this design. And that's an important term to remember, that contour lines represent changes in elevations. So here our contour line on point A shows that we are at an elevation of 100 feet. Our contour line on B shows we're at an elevation of 105 feet. Our contour line on C has us at 110 feet. And our contour line on D has it at 120 feet. So those are our changes in elevation on this plan. And regarding the formula, that would be our rise. An example would be from point A to point B. We've got 100 foot and 105 feet. So our rise is going to be 5 feet. From point A to point C, we have 100 feet at point A, 110 feet at point C. So our rise is going to be the difference between the two, or 10 feet. From point A to D, we have 100 foot at point A, 120 foot at point D. So our rise is going to be the difference, which is 20 feet. So that's going to go at the top of our formula, will be the differences in elevation represented by the contour lines, which we will call the rise. The second half of our formula is the run. To calculate the run between these points, we'll have to use our 1 to 20 scale. The run will be laying your scale from point to point and taking a measurement. So here we have point A and point B, and this is showing to be on a 1 to 20 scale. So if you take out your scale and measure from point A to point B on your 1 to 20 scale, when you put your scale and measure from point to point, you should get that to be 34 feet. So this green line from A to B represents 34 foot of run. Let's do our first example and continue on with these calculations. So our first question would be, what is the percent of slope from point A to point D? Our formula is to take the rise over the run. From A to D, we have point A is right here at 100 feet. We have point D is right here at 120 feet. So the difference is 100 subtracted from 120 is 20 feet. So here is our rise, 20 feet. On the bottom will consist of our run. Our run from A to D, here is point A. We draw a straight line to point D. Now we need to measure from this point A to this point D in our 1 to 20 scale. So get out your 1 to 20 scale and put your 0 on point A, and come over here to point D. And on your 1 to 20 scale, the distance from point D all the way to point A should measure approximately 93 feet. Now we can do our calculation on our calculator. On the top is our 20 feet. On the top is our 20 feet, which is our rise. On the bottom goes our 93 feet, which is the run. So in your calculator, you'll enter 20 divided by 93, which will give you 0.215. That's a decimal form. So to convert that to slope in percentage format, we'd say that is an approximately a 22% slope from A to D. Now we'll do our second example on calculating percent of slope, which is going to be going from point B to point C, calculating percent of slope. So here's point B, here's point C. Our contour line shows we have 105 foot of elevation at B, 110 foot at C. So in our formula, which is to take our rise over the run from B to C, Our rise is going to be 110 subtracted from 105 will give us a 5-foot run. So from B to C, we'll have a 5-foot rise. Once again, 105 foot of elevation, 110 foot of elevation gives us a 5-foot difference, and that's going to be a 5-foot rise in elevation. So we'll go on the top of our formula, 5 foot. On the bottom of the formula is going to be our run, and our run is going to be measured from point B to point C. So with your 1 to 20 scale again, put your 0 at point B and measure over to point C on your 1 to 20 scale. And you should get a measurement of around 33 feet from point B to point C. That is going to be our run. So on the bottom will be 33 feet. So our percent of slope from B to C will be a 5-foot run, a 5-foot rise over a 33-foot run. On our calculator, you'll take 5 divided by 33, which will give you a decimal of 0.151. Or an approximate percent of slope of 15%. Our next percent of slope we'll calculate is here, which is from A to C. So here we have point A, and here we have point C. We have 100 foot of elevation according to our contour line at point A, and 110 foot of elevation at point C according to our contour line. So from A to C, we have a 10-foot rise. So A to C, our formula is going to be a 10-foot rise divided by our run, which from point A, we'll take our 1 to 20 scale and measure a line directly to point C. Taking your 1 to 20 scale and putting your 0 at A and measuring over to point C, your run should measure approximately 68 feet. So in our calculator, we'll take our 10-foot rise and divide it by our 68-foot run, which will give you 0.147, which can convert to an approximate 15% of slope. Our next percent of slope calculation is going to be going from point B to point D. Here we have point B, and our contour line is showing to be 105 foot of elevation. Going to point D, our contour line shows 120 foot of elevation. So from B to D, our rise is going to be 105 subtracted from 120, which is a 15-foot rise. Our run is going to be from point D from point B to point D a measurement. So with your 1 to 20 scale, put your 0 on point B and measure over to point D. And you should get approximately from point B to point D a 60-foot run. So on the bottom of our formula will be our 60-foot run. So in our calculators, we'll take our 15-foot rise divided by our 60-foot run, and that's going to give us a 0.25, or an approximate 25% of slope. Now we'll go to our last calculation on percent of slope. Here we're going to go from point A to point B and use our formula, the rise over the run. Here we have point A, and our contour line shows that we're at 100 foot of elevation. Here we're at point B, and our contour line shows we're at 105 foot of elevation. So from A to B, in our formula, our rise is going to be 5 foot. Our run from A to B is going to be a straight measurement from point A to point B. So if you take your 1 to 20 scale and measure from point A to point B, you should get approximately 34 feet. So our run on the bottom is going to be 34 feet. So in our calculator, 5 divided by 34 gives us 0.147. Converted to decimal is about a 15% slope. Now we're going to review the 3 ways to calculate safe flow for your irrigation system. What we're going to start out with is to give you some information on a sprinkler system by letting you know there's a 3/4 inch meter with a 1 inch copper service with 70 pounds of static pressure on a job site. So given that information, what we're going to do now is determine the safe flow for your irrigation system. The safe flow is sometimes also referred to as the design GPM, which stands for gallons per minute. We're going to be reviewing a few formulas that we'll just call the safe flow or design gallon per minute formulas. First, we're going to start out with the pressure. So given that we have 70 psi, we're going to use this formula to determine the safe flow through the meter. The first thing we're going to do is take our pressure and multiply it by 10%, which gives us 7 psi. Then we're going to bring down our 70 psi and subtract the 7 psi that we just calculated, which is going to give us 63 psi. And now we'll bring down our 63 psi and multiply that by 10% again, which gives us a 6.3 psi. So once again, to review, when you take a static pressure to determine safe flow through your meter based on the static pressure, we'll take our static pressure, which in this case was 70 psi, multiply it by 0.10, 10%, and get that figure, which comes out to 7 psi. Then we'll take that 7 psi and bring it over and subtract it from the original static, which was 70. So 70 minus 7 psi gives us 63 psi. Then we'll take our 63 psi and bring it down and multiply it by 10% again to get our final answer, which is 6.3 psi. What we do with this answer is we want to make sure that we do not exceed a 6.3 psi loss through the meter. And in this case, we told you we had a 3/4 inch water meter. So now we'll have to turn to our water meter charts and go to the 3/4 inch size water meter and come down on our pressure losses. And our goal is not to exceed a 6.3 pound loss through that 3/4 inch meter, and that will give us a safe design gallon per minute for our meter. So get out your pressure loss charts and turn to the meter chart. Here's our meter chart. On the top here, it says water meter. And we told you that there's a 3/4 inch meter, so here's our size as a meter. Here's our 3/4 inch meter. And we said we don't want to lose more than 6.3 pounds. So here is our pressure losses on the meter. And we start going down our pressure losses on this meter. We'll come down at 1 pound of pressure loss on the 3/4 inch meter. Our flow is 8 gallons a minute. We keep on coming down. Here we have a 5.8 pound pressure loss, and at 5.8 pounds, our flow is 19 gallons a minute. Now we go to 6.5. So we just exceeded our 6.3 calculation. So we don't want to go there. If we go to 6.5, we can flow 20 gallons a minute, but we're over our 6.3 maximum pressure loss through the meter. So what we want to do is go back to the 5.8, so we do not exceed our 6.3 loss, and come across to the left and find our safe flow through a 3/4 inch meter when we're running 70 psi static pressure would be 19 gallons a minute. So back to our original question, at 70 pounds of static pressure, our safe flow is going to be 19 gallons per minute. And that's based off 70 psi. Next, we're going to come up and do our 1-inch copper service. So our second way to calculate available flow is going to be by the copper service. And we say we have 1-inch copper service. So now we're going to have to turn to our copper chart to calculate the safe flow through copper. So turn to your copper chart. On the copper chart, you'll notice we have the different sizes of copper across the top. And we had said 1-inch copper is a service on this design. The rule of thumb on this copper chart is not to exceed 9 feet per second velocity. So on our 1-inch copper, here's our velocity column. When we come down our velocity column, we can see when we get to the shaded area, we're over 9 feet per second. Here we're at 8.24 feet per second. When we come across to the left, we'll see that that is at 20 gallons per minute. So that's the maximum flow through 1-inch copper based on not exceeding 9 feet per second velocity. Again, we'll come down to the velocity column. We don't want to exceed 9 feet per second. When we get to the shaded area, that's where we go over 9 feet per second. So we'll come back. Our last highest velocity before 9 feet per second is 8.24 feet per second. We'll come across to the left. This is our gallon per minute column. And when we come down our gallon per minute column, we'll see our maximum flow, our maximum safe flow is 20 gallons a minute on the copper. So on the copper, 20 gallons per minute. So now we'll go to our third formula for safe flow, which would be based off the meter. We have a 3/4 inch meter. Our formula for safe flow through the meter is to take our maximum gallons per minute through the meter times 0.75. So that's going to be our formula in determining how many gallons will safely flow through that meter. So we'll have to go back to our meter chart now and look up on a 3/4 inch meter what the maximum gallons per minute that will flow through that meter are and multiply it times 0.75. So here we are back at the meter chart. Here's our 3/4 inch meter, and these are our pressure losses. We come down on this column, our last pressure loss is 11.2 at 26 gallons per minute. Now on this chart, there's another column right here for 3/4 inch meter that continues on. And we can see our last pressure loss on a 3/4 inch meter is 15 psi, which corresponds with, right here, 30 gallons per minute. So our maximum flow through that 3/4 inch meter is 30 gallons a minute. Again, to find the maximum flow on the meter, you'll go down your pressure loss column until the last pressure loss is shown, which on our 3/4 inch meter, on the first column it stops at 11.2 psi of pressure loss, and then it starts again right here and comes down to 15 pounds of pressure loss. So that's our maximum loss. Then we'll go across to the left to find the corresponding maximum gallons per minute. So on the 3/4 inch meter, your maximum flow is 30 gallons a minute. So I'll put that into our formula. Our maximum gallons per minute is 30 gallons per minute. We'll multiply that times 0.75, which comes out to 22.5 gallons per minute. So that's going to be our answer for a 3/4 inch meter for the design gallon per minute, or safe flow through the meter, 22.5 gallons per minute. Using this design gallon per minute formula, which is to take the maximum gallons per minute of the meter times 0.75. So we can put that in on our meter. We have 22.5 gallons per minute. So to wrap it up, to get our safe flow, design gallon per minute, based on having a 3/4 inch meter, 1 inch copper service, and 70 psi, our answers would come out to, on a 3/4 inch meter, our safe flow is 22.5 gallons per minute. On a 1 inch copper service, our safe flow is 20 gallons a minute. With 70 pounds of static pressure, our safe flow is 19 gallons per minute. From here, you'll have to use your common sense and irrigation knowledge to select which one of those 3 gallon per minutes will work well on your design. Continuing reviewing some of the fundamentals of irrigation design, now we're going to talk a little bit about elevation and calculating dynamic and static pressures. Go ahead and get out the handout included in your packet. Then the top has the letters A, B, C, and D on it. And we're going to review the information given to us and determine some calculations. On this sheet, it says that you have 4 points, A, B, C, and D. It says A has an elevation of 400 feet with a dynamic pressure of 80 psi. B has an elevation of 415 feet. C has an elevation of 450 feet. And D has an elevation of 475 feet. So on your paper, let's go ahead and draw these elevations out. It says that point A has an elevation of 400 feet and has a dynamic pressure of 80 psi. it says point B has an elevation of 415 feet. Point C has an elevation of 450 feet. And that point D has an elevation of 475 feet. So go ahead and draw out those 4 points along with me. Also, on that handout, it says on our lengths of pipe from A to B, we have 25 feet of pipe. So from point A to point B, we have 25 foot of pipe. From B to C, from point B to C, we have 15 foot of pipe, and from C to D, we have 50 foot of pipe. So let's go ahead and draw in the pipe on this example also. And the question asks, what is the dynamic pressure at B, C, and D if there's 30 gallons a minute flowing through 1.5 inch PVC pipe on this drawing? So one thing we'll have to do is determine our friction loss through that pipe and determine any elevation gain or loss based on the elevation differences in order to determine our answer. So we'll have to get out our Class 200 PVC pipe pressure loss chart. So now we turn to our Class 200 PVC pipe pressure loss chart. We can look up on our 1.5 inch pipe at 30 gallons a minute how much pressure we'll lose per 100 feet. So here's our 1.5 inch pipe column. Here's our gallons per minute column. When we come down to 30 gallons a minute, and we come over to 1.5 inch pipe, we can see at 1.5 inch pipe at 30 gallons a minute, we lose 1.65 psi per 100 feet. So going back to our original question, where it said that there's 30 gallons a minute flowing through the 1.5 inch pipe, which is going to be this pipe, this 25 foot of pipe, this 15 feet of pipe, and this 50 feet of pipe. we know that we lose 1.65 psi per 100 feet. 1.65 psi per 100 feet and 1.65 psi per 100 feet of pipe. We'll have to do a calculation to determine the actual loss, because this is only 25 foot of pipe, this is only 15 feet of pipe, and this is only 50 feet of pipe. But now we have our figure to go off of, that we lose 1.65 per 100 feet. Now we can begin doing some of our calculations at these different points to derive our answers. So at point B, which is at 415 feet, if we wanted to calculate what our dynamic pressure would be, we'd have to use our formula. So at point B, our dynamic pressure formula would be to take our 80 pounds of dynamic pressure, which is at point A, and subtract our TL, which would be our total loss. We have two different total losses. One is elevation, which we have 415 feet at point B and 400 feet at point A. So we have a 15-foot elevation difference. 415 feet minus 400 feet means we have a 15-foot elevation increase. So to determine our pressure loss, we take our 15 feet times 0.433, which is going to give us 6.49. And that 6.49 is going to be a pressure loss because the water is going uphill 15 feet. And when the water travels uphill, we lose pressure. The other pressure loss we're going to have is going to be in our PVC pipe. It says we have 1.5 inch pipe from A to B, and it's flowing 30 gallons a minute. So we talked about earlier, we're going to lose 1.65 psi per 100 feet. So we're going to lose 1.65 psi per 100 feet. We only have 25 feet of pipe from A to B, so we'll multiply the 1.65 pressure loss per 100 feet times 0.25 on our pipe. We'll have to take a percentage of 100 foot, so 25 feet would be like 25%, or 0.25. So 1.65 times 0.25 gives us a pressure loss of 0.41. So we have two pressure losses. One would be the elevation loss of 6.49, and the other would be the pipe pressure loss of 0.41. So when we add those two losses together, the 6.49 plus the 0.41, our total loss comes up to 6.90. So to calculate our dynamic pressure at point B, our formula is dynamic pressure equals 80 minus the total loss. So our total loss is 6.90. So 80 subtracted 6.90 gives us an answer of 73.10 for our dynamic pressure at point B. Now we can move on to calculate dynamic pressure at point C. Here at point C, we have 450 foot of elevation. Our original elevation back at point A was 400 feet. Once again, we'll go ahead and write out the formula to get our dynamic pressure. The formula for point C for dynamic pressure would be dynamic pressure equals our original dynamic, which was 80 at point A, minus our total loss. I'd always go back and use our original dynamic pressure of 80 psi as a starting point to ensure the correctness of all answers. Once again, we have two pressure losses we'll have to be concerned about to get our total loss. One would be our elevation. Here at point A, we have 400 feet. Here at point C, we have 450 feet. So we have a 50-foot elevation difference between point A and point C. And that elevation is going uphill, so it's going to be a pressure loss. So we have 50 foot of elevation difference. We'll multiply that times our 0.433, which gives us a total pressure loss of 21.65. And once again, that's the elevation pressure loss from a 400 foot elevation to a 450 foot elevation. The other loss we're going to have is through our pipe. And we talked about it earlier, all this pipe is 1.5 inches, class 200, running 30 gallons a minute. So we looked that up, and right here we said we lose 1.65 pounds per 100 feet. So our other pressure loss calculation is going to be 1.65, which is our per 100 foot loss, and we'll have to multiply that times a percentage of the 100 feet we have. So from point A to point C, we have 25 feet of pipe from A to B, 15 feet of pipe from B to C. So our total pipe is 40 feet. So we'll take our 1.65 times 0.40, and again the 0.40 is a percentage of our 100 foot loss. So our 1.65 times 0.40 gives us a 0.66. And we'll add these two pressure losses together. 21.65 plus 0.66 gives us a 22.31 total pressure loss. So we need to subtract our total loss, which is 22.31, from our 80, which is going to give us a dynamic pressure at point C of 57.69. Now, moving on to the dynamic pressure at point D. First, we'll have our formula, which is our 80 pounds of original dynamic pressure minus our total loss. We'll have our elevation difference, which we have 400 feet at point A, 475 feet at point B. So 75 feet of elevation change times 0.433 gives us a pressure loss of 32.47. And then we'll have our pipe loss, which we lose 1.65 psi per 100 feet. We have a total of 90 feet, which is our 25 feet, plus our 15 feet, plus our 50 feet. So 1.65 times 0.90 gives us a 1.48 loss. And we'll add our 32.47 into our 1.48 loss, which gives us a total loss of 33.95. and then we'll take our 33.95, which is our total loss, subtract it from our 80, which will give us a dynamic pressure at point D of 46.05. Now continue on to Disc 2 to continue reviewing irrigation design fundamentals, or review this disc as much as needed.